Hi, my name is Joe, and along with Caden, Raul, Paul, Sean, and Tim, we are Team 5. We are looking at the analysis of the Dayton 6Z846 drill press vise. Drill press vices can be bought in most hardware stores, as well as bought directly from tool and equipment retailers. The primary customer group defined for our product was machinists and machine shops, who use vices professionally, and then the secondary customer group was defined as hobbyists who use the vice occasionally to secure parts for home projects and such.
Here we see an exploded view of the drill press vise assembly, along with labeled part numbers and names that we will reference throughout the rest of this video.
To ensure we have a comprehensive understanding of the drill press vise function, our team performed a functional analysis system technique diagram to determine the why and how relationships that connected the functions of the device. Taking a look at our diagram, we determined that the primary function of the device is to hold components that are to be drilled. In order to hold the components, the device must be able to both secure and release the components. Securing the component must be done by maintaining a consistent grip force and by preventing motion of the component while being drilled. In order to release the component, the grip force must be controlled to slowly release the part from the vise. Releasing the component must also be done by allowing motion. Secondary functions of the drill press vise include assuring dependability and convenience, enhancing the product, and pleasing the senses. In order to assure dependability, the product needs to reduce any slipping that may occur to prevent misaligned holes being drilled. The drill press vise itself must not also vibrate so as not to cause misalignment of the component relative to the axis of the drill.
To determine the impact of a potential redesign of the vise, a function component mapping matrix was generated. If a component helps the overall assembly realize a function, it is marked with an X in the matrix. Using the function component mapping matrix and the bill of materials, parts that are candidates for redesign can be determined. The matrix shows the importance of a part, while the bill of materials shows a component's cost. Having a high importance and low cost is ideal. The combination of high importance and high cost results in a need for redesign, while having low importance results in elimination or combination of parts.
All functions in the function component mapping matrix were classified in one of two categories. Being that we're dealing with a product family design, we are dealing with the differences for each customer group, which are prevent motion, please senses, and prevent vibrations. In the function component mapping matrix, a part that is associated with a function's pleasing senses, prevent motion, and prevent vibration is the jaw plate. Furthermore, in looking at the bill of materials, the jaw plate is an inexpensive component in absolute terms that, if modulated, can provide a benefit to the customer by providing additional utility of the vise without further major design considerations. The additional utility to the vise would come from varying abilities of each different jaw plate. The ability of properly attaching and or milling an object on the vise depends on the geometry and material properties of the jaw plate holding the object in place.
For the primary customer group, factory workers and professional machinists in machine shops that use drill presses for a variety of specialized products, shapes, and sizes, it's advantageous to have multiple vise grips of varying jaw plate shapes and textures that better support and secure the workpiece when making professional machine cuts. That is why we designed 4 different variations of the jaw plate to differentiate between the functions more important to professional machinists and secondary customers who are hobbyists who use a drill press for smaller projects and don't need the level of precision. Based on the original assembly sequence, we created this product family assembly diagram, where the branches are product variants and the nodes represent the addition of components. With the 4 variations of jaw plates, each branch of the assembly tree requires the assembly of all the remaining components. We then modified the assembly sequence in order to take advantage of delayed differentiation. The jaw plate is now assembled last, so cost is reduced now that only 1 production line is needed for the assembly.
Based on the assembly sequence in the product family assembly diagram, an assembly analysis of the primary product variant was conducted to calculate the total assembly time and efficiency. Process 11, adding the key, was chosen as the process for adding a platform part with relatively high assembly time. Process 15, adding the jaw plate modules, was chosen as the process for adding a module with a relatively high assembly time. For the platform parts redesign, the collar and key were eliminated since they were not vital to the operation of the drill press vise. The end of the vise screw will now provide the force against the sliding jaw to clamp onto parts. This was suggested by Design for Product Handling 3. Avoid parts that are easy to tangle or nest, which applied to the key, and Design for Assembly System 1, minimize part counts. Chamfers were added to the sliding jaw and vise screw to aid in hole location, as suggested by Design for Part Insertion 1, add features for easy insertion. The before and after CAD views are shown here. Next, for the module parts redesign, the jaw plate screws were eliminated by adding in a dovetail interface, as suggested by Design for Assembly System 1. Additionally, the dovetail interface allows for assembly from the top, suggested by Design for Part Insertion 3. Finally, chamfers were added to the dovetail mounts on the base and sliding jaw, as suggested by Design for Part Insertion 1. A before and after CAD view is shown here. Finally, another manual assembly analysis was conducted to find the total assembly time and manual assembly efficiency of the assembly after redesigns. The results are good. The number of parts in the assembly decreased from 20 to 14, the total operation time decreased by 51.8 seconds, and the manual assembly efficiency saw an 11% increase.
The vice screw subassembly contains 6 lightweight parts that can be automatically fed, oriented, and inserted. This is an analysis of the parts of the vice screw subassembly. The original design has a handling cost of 2.1 cents and an insertion cost of 2.18 cents. The vice screw subassembly is shown before on the left and after redesign for automatic assembly on the right. The subassembly has had its part count reduced from 6 to 3, as minimizing part count improves the assembly system. The old design required turning over and precisely orienting parts to align holes to insert a pin, and the new design is able to be assembled along one axis. Finally, a chamfer around the hole of the new knob was added. This feature will allow for easier insertion, guiding the handle rod into the hole. This is an analysis of the redesigned vice screw subassembly. The handling cost is 1.43 cents and insertion cost is 1.37 cents. The comparison of costs before and after redesign are shown in the table. The handling cost was reduced by 0.67 cents and the insertion cost was reduced by 0.81 cents.
Fully dimensioned engineering drawings were made for the redesigned jaw plate and vice screw, with critical dimensions and tolerances called out in order to select the proper manufacturing process and material for each component. The dimensions of the jaw plate were fully defined, with a dovetail opening compatible with the base and sliding jaw. The part's only critical dimension was the 100 thou plus or minus 2 thou dovetail opening for the installation of the jaw plate. The vice screw was fully dimensioned, and the custom threads and screw end diameter were determined to be critical. The vice screw had a custom thread callout, and the diameter of the end was 500 thou plus or minus 1 thou.
To ensure our product was sufficiently stable and durable enough to withstand large forces while clamping for the jaw plate and tightening for the vice screw, we determined that both components should be made from alloy steel. From here, we applied the appropriate constraints related to product material, shape, mass, section thickness, tolerance, surface roughness, and batch size to determine the optimal primary and secondary manufacturing processes. As you can see, the two processes that met all criteria for both parts included powder methods and conventional machining. However, powder methods alone would not be precise enough to meet the tolerance of the dovetail on the jaw plate and the threads on the vice screw. While precision machining proved to be a viable secondary process for both parts and could be capable of producing quality components in conjunction with powder methods, we decided to use conventional machining as our selected manufacturing process to eliminate the need of a secondary process for our alloy steel jaw plate and vice screws.
Performing cost estimation for manufacturing the vice screw at the primary process, we obtained that the vice screw costs $3.57 per part in a batch of 2 million units. As shown in the isometric sketch of the vice screw, there are 3 modified features from redesigning the primary process. The first feature change was the geometry of the screw head following DfM 13. The second feature change was to make the dimension of the through hole standardized to a drill bit size P following DfM 3. The third feature change was to run the threads all the way from the shoulder to the head of the screw following DfM 14. In performing cost estimation for manufacturing the redesigned vice screw, we obtained that the vice screw cost $3.52 per part in a batch of 2 million units. The redesigned vice screw is 5 cents cheaper per part than the primary vice screw.
To redesign the jaw plate for manufacturing, first the cost is estimated. In this estimation, we assume the base stock is pre-cut into 2-inch by 3-inch blanks before going into the milling machine, and the original cost for making one part came out to be $2 per part. 3 design changes that we made to make the part more manufacturable are: we changed the plate thickness to exactly 3/16 to match stock size using DfM 2. We changed the dovetail dimensions to match at a standard dovetail bit using DfM 3, and we made the dovetail less deep and moved it away from the edge using DfM 9. And then using these design changes, we estimated the cost again using the same assumptions as before, and this came out to be now $1.84 per part, which comparing to the previous $2 means we save around 16 cents per part.
A monthly membership fee could be integrated into the product family to form a product service system. All customers would buy the drill press vise that comes with the standard jaw plates, and they could pay a monthly fee for a membership which grants them access to different jaw plates. There would be a phone service and 24/7 website chat feature to help customers determine which product variant best suits their needs. Once additional jaw plates are selected, they're shipped to the customer, who can then return the old one whether it's damaged or not. The customer can leave a product or service review for continuous improvement, and they would then receive a trade-in credit on the monthly membership fee. Compared to the product family without the service, customer experience would be improved because they do not have to purchase individual jaw plates. Instead, they have access to as many jaw plates as they want for a monthly fee. Also, they get expert advice, and if one breaks or gets worn down, they can return it and save money. This also reduces negative impact on the environment, as it encourages recycling of jaw plates and less total materials used in the long run, which could decrease carbon emissions from mining and transporting raw materials. In conclusion, the overall benefits gained from the redesign are 9 fewer parts, 38 cents less expensive to manufacture and assemble per unit, an 11.1% increase in manual assembly efficiency, a product family with different jaw plates, potentially a product service system to allow users to have access to all product variants, help over the phone, decreased carbon emissions, and overall a less complex design. To self-critique our design, yes, it has fewer parts and is more streamlined, but the rotating vice screw makes direct contact with the sliding jaw, and the sliding jaw does not come unscrewed with the vice screw. To further improve this design, we could eliminate the slide keys and set screws since they take 40 seconds to assemble. To approach this differently, if we were to start over, we would aim to eliminate the slide keys and set screws and allow the sliding jaw to retract along with the vice screw.